Welcome. This is the part Programming Languages for Big Data from the Interdisciplinary Center for Applied Machine Learning. When you're working on machine learning, you're at the same time working on big data. And there's several choices of programming languages that make sense. When you're a beginner, you should of course choose wisely which programming language to learn. So what we intend with this part, with these slides, basically is to show you the most important programming languages and their use cases such that you can select what to learn when. So first think about yourself. The first question you should ask is, what is your favorite programming languages? What do you like about the programming language you know? What do you dislike? And then look at the list of programming languages that I think are most important in the big data area. So these are Python, R, MATLAB or Octave. MATLAB is a matrix programming language and Octave is the free clone. MATLAB is of course a little bit cleaner as it's commercial and it runs perfect and has a lot of toolboxes. Octave is kind of a clone of MATLAB. It works very well and it's also very fast, but the toolboxes are kind of missing. C++, Java and Scala. And of course, there are some more specific languages for specific context. But if you know these languages and if you're excellent in one of those, you are well into big data. Let's look at those languages. The first language, of course, is Python. Of course. Why of course? I mean, the advantages of Python are it's a nice modern scripting language. So it has some modern constructs like lambdas. It's very easy to write and read. It's efficient for scripting because it does not have annoying syntax like catching all exceptions. Of course, catching all exceptions increases kind of software quality the Java way, but it also makes the code a bit difficult to read because there's so much bookkeeping involved. For Python, huge amounts of software are available and well integrated because Python is so C++ friendly. It's extremely easy to write C++ code and to interface this from Python and vice versa. But there are also some drawbacks. Sometimes Python can be difficult to read depending on the style. For example, Python has this very nice syntax of bracket expressions where you can basically have a complex for loop or a typical for loop pattern where you have a loop, you have a condition inside the loop, and you have a result. And this can be put into a bracket. And these expressions can be put into each other, and then it gets really ugly without good comments because there is then no place to put your comments really. So sometimes bracket expressions written by other people, they are very difficult to understand. Software quality can be an issue, but we are in the big data area, so most of our software is rather sketchy. So when you do machine learning, you don't need highest software quality. And especially for Python, there's huge amounts of software available, which means also that the quality of the available software varies. And it's easy to break. This is possibly, for beginners, one of the worst things. When you use your operating system Python on a Linux machine and you install some stuff and then you try out something else from GitHub, possibly from the past, then sooner or later you run into conflicts where you have old versions of packages, new versions, some dependencies that are actually not working anymore. And because of these problems, there are some things that have been done. For example, virtual environments. You can basically have several completely independent Python installations on the same machine. And this is what you should do when you are only into Python. Otherwise, you can, of course, also isolate using Docker, which gives you even more isolation, where you don't need to install all the operating system libraries onto your host computer, and you can get your software running even with different versions of Python and whatever. And there is one thing I really don't like. When Python 3 was invented over Python 2, some things really changed. So that even though a Python 2 program might run in a Python 3 environment with very small changes, might not do the same. Then the programming language R. This is a very classical language with excellent documentation. And this is one of the advantages, of course. And as this was like a clean functional language, it's based on the S language, you have kind of uniform names for all common actions. You have things like fit, model, predict, plot. So when you, for example, train a machine learning model, say a model of type A, and you use fit and predict on this, you can just exchange the model by a different model B. And the same for the plot. The plot will usually select the most sensible representation of the model you have and will plot it. So basically the meaning of these functions depends on the data you give or on the model you're actually using. This makes it very clean and very easy to use foreign software, like downloading the fanciest new model. It will have an interface according to S language with functions like fit and predict. R is extremely C++ friendly. So R itself is friendly with respect to C, but it's a bit tedious with memory management and with these S expressions that are basically the core of the implementation. But some people build RCPP, which is basically an R package that has a lot of nice sugar so that you can write very, very clean C++ code and get it automatically put into your current R session. So you can write a C function or C++ function inside the R file just by compiling it there with a single statement, or you can put it into a library. And what's very good about the C++ stuff is that on the Windows operating system, the RTools package gives the compiler so that you can expect to have compatible compilers across all platforms. That is, when you distribute your C code in source, it will work. You are not bound to using or to crossing between Microsoft Visual C++ and some GNU compiler or some Clang compiler for the Linux and Unix. Okay, it has very good plot defaults for scientific computing. If you want to show something on a screen, the defaults of Python are very good, but often they have the same intensity for the different things. So when you turn this into grayscale, for example, when printing, all the colors become more or less the same. R is kind of the opposite. It's not very beautiful on the screen. It's just mainly black and white, but it's of course extremely good for scientific publications. It has a nice IDE with RStudio. For example, when you're on Windows, just download the RStudio installer and get yourself started. And R has a very, very good peer-reviewed source code repository, the CRAN, the Comprehensive R Archive Network. And the good thing is that these packages consist usually of three aspects. One is, of course, the package, most often including the full source code, so you can dig into the details. Then something called vignette, which just shows how to use the package. Usually it's just an example case with comments, and very often also a paper, sometimes published in a journal, so that you can actually cite the implementation. Because very often there is a difference between the rough name, when you say this implements a linear model, and all the choices no one talks about. So you will have correct implementations with different behavior. In this case, when you can, of course, cite the exact implementation through citing a paper that's bound to an R package, you have said very clearly what you mean. And what's very good is, of course, that it has a functional core. Why this is important will be explained later in more detail, but for now let's just say a functional programming language works just by functions. So basically there is no distinction between data and functions, and what this means usually is that many functions don't return some work that has been done, they return a function that could do the work. This is known as lazy evaluation. And for the big data case in spatial computing, for example, this means when you have a gigabyte size TIFF file, some image, and you just load the image, nothing will be done at this point in time. But when you access the image, You have to access it via functions because it's a functional programming language. And the open call in this case will have returned a function object that will take care of loading. So when you only consume a very small part of the file, you will not load the file. So what this means basically for you as a programmer is that all the bookkeeping that you would need in an imperative programming languages in order to open the file in some point of code and then only when you need it, execute it. This is kind of automatic. And there are, of course, some drawbacks. Functional programming languages, it's not the easiest to start with. While the R language has taken a good deal of work into letting R look like an imperative language to make it easy to start with. Of course, you cannot unlock all this coolness of functional programming when you are not a bit into it. And of course, it's also sometimes difficult to read due to complex statements. You will learn that when you look at our code. So the third language is actually a language pair. It's MATLAB, the commercial one. It's a matrix-centered multi-purpose programming language. MATLAB comes with a matrix core, basically, so a language where you can do all types of matrix vector operations. And it has lots of toolboxes for different aspects you might need. For example, a signal processing toolbox, a communications toolbox for the communication engineers, a deep learning toolbox. So basically you define what you need by choosing the right toolboxes. They're computer vision toolboxes, excellent commercial software with support, well documented and quite fast. And there is the open source variant, it's Octave. It's basically only the core of R, while there is Octave Forge, where people are working into getting some aspects of the most important MATLAB toolboxes into the Octave world, but it's far behind, right? It's very, very good if you are in a field where most people are using MATLAB, so mostly the engineering fields. It has several drawbacks, of course. It's very expensive if you need to buy it for commercial purposes. It's not cheap. It's not open source, which is sometimes a drawback when you really want to dig into what exactly has been chosen for implementations. While it has a very good documentation, you're not absolutely lost, but sometimes you might be interested in a very, very small detail, and you cannot dig through the source code as you could do in an open source environment. And of course the drawback, if you are into MATLAB, you might want to have the real MATLAB with the license, because the open source version is not fully equivalent. C++, kind of the most important language in computing. Not for everyone, but it's basically the backbone of computing. The advantages are it has relatively high performance. There are some faster languages that are being used, like Fortran, which can be actually faster. You can show this. There are some properties of C, like the pointer overlap, that make it slightly slower than Fortran. But the C++ world has extremely high quality libraries, mainly through the Boost projects. You can look at it. It has full platform independence, so when you want to adopt novel techniques or mobile or edge computing or embedded, C++ or at least C runs on nearly every microcontroller, and you can implement your CPU, GPU, whatever code in C and C++. It's embeddable into Python, Java, R, and MATLAB, so it bridges almost everything. Sometimes it's not easy or not the best way of extending something. For example, when you want to embed it to Java, you can use the Java natives, but there are some drawbacks when you don't have direct memory access, where it's not the easiest, but it's a first order citizen for Python and R. So when you are into C++, you will soon implement your core algorithms, the thing you really care about in C++, and use Python or R, depending on the context, to do all the interfacing, including plotting and whatever. And it has full support for generic programming, so when you learn it right and when you have experience, you can write your algorithm in terms of concepts. So you write it exactly once, crossing all the mentioned programming languages. And it has a very modern standard. Now C++ 17 has been it's ready. Not all compilers support it, and when you just install your favorite Linux, I'm pretty sure you have an older compiler that does not support it yet, but you can of course always download the newest compiler. Just look into these standards, because you then see a lot of features that other programming languages just cannot provide. What are the drawbacks of C++? The compiler errors are very difficult to read, especially when you are using generics. Because in the case of generics, you're not fixing the types. So what the compiler actually does is it spots an error, and then it tells you what it believes about all the types. And this can be really a screen full of things the compiler believes before he is able to actually give the error. And you have to kind of find out whether you have just been using the wrong types with the wrong functions, you have implemented something wrong in the template logic, or whether you have just missed a semicolon. So you need experience, you need patience when you want to start with this, but it's worth it, because you're not going to write very large projects in C++ anymore. You will write the core algorithms, and then you can use them from Python, you can use them from R, you can use them from MATLAB. So it's really something to have a basic understanding. And another drawback comes more from history and backward compatibility. I mean, there's so much C code outside, and most of the C code is still in use, and some of the C code is really excellent. So you need to have the compilers backward compatible, and sometimes this is impossible, and this starts to change things. So then one compiler is going the left way around the problem, and another compiler the right way. One example is that Microsoft C++ removed all the insecure C functions, like string copy without giving a length, and renamed them to something else, while they are still there in the old name in all GNU compilers, and possibly just giving a warning that you should not so much rely on these functions unless you know what you're doing. This leads to source code when you want to have it portable, which checks actually for the compiler and provides some slight corrections until your own code really works. So this is some drawback, but for the big data area, you can safely stick to the GNU C compiler because it runs on Python. It's the compiler behind R, and you can use it on Windows quite well. So possibly you can just avoid this by choosing your own favorite compiler. Java, a language we cannot miss here because it has a good performance. Many people say Java is very slow, but this is not really true. It's true for very certain workload types. In general, it has good performance. It has a very high quality design and runtime, which is good for beginners because it's easy to understand. It's not fragmented. It's very clean. It has a sort of platform independence. The type of platform independence you can also have for most of the other ones. In the case of Java, you have some bytecode, which is kind of the binary of Java, and you have to install the Java runtime on all the machines where it should be running. However, Java is so important that it's installed on most personal computers anyway, and it's not so hard to install and manage on a remote computer. Nowadays, you can do the same with almost all Linux software too, through Docker. So the platform independence depends a bit on what you mean by this. But you can easily cross platforms like 32-bit, 64-bit, and whatever. It's easy to learn mainly because it has very good error messages, right? As the language has been designed very cleanly without a C in the background like with C++. And as you have to catch all exceptions, the errors are kind of very clean. So this is why many universities adopted it in the beginning, because it's a clean language with full functionality where you can teach very well in. It has a very safe memory management system, which can be, of course, an advantage if you don't have too memory intensive or memory fragmented workloads. The garbage collection, that's kind of taking care of the memory management, which is a little bit out of control of the programmer in the first moment, can of course also hurt the performance. So these are the drawbacks basically. You're unable to unlock some aspects of modern computers like GPUs or specific instructions because your source code mainly relies on the bytecode that has been standardized some years ago. And there are just-in-time compilers that can use these instructions, but you have to think about the fact that the just-in-time compiler must be fast enough to unlock those. So if you have extreme workloads, it might be that a just-in-time compiler is not able to compile just-in-time to the same quality as an offline compiler could do. And the overhead produced by memory management can hurt you, especially in very fragmented situations when you, for example, have very, very small classes and very many instances, and you create new ones and delete old ones very often. Then garbage collection can be a real overhead. And as Java is kind of a very safe language, it's often used in distributed computing, but it has some drawbacks with respect to data-driven computing. There needs to be a functional language for the JVM, and this is exactly Scala. So Scala is a functional programming language on top of the JVM, of the Java Virtual Machine. So everywhere where Java is already running, you can run your Scala programs. And it has basically the same possibilities as Java. You can extend it with Java. So if you implement your algorithm in Java, you can apply it in Scala. And Scala has been chosen for many of the big data frameworks as one of the main languages. For example, you can use Scala in Spark very well, in Apache Spark. So when you are into the cloud computing aspects of big data, then Scala is definitely a language to know. But it has the same drawbacks inherited from the Java Virtual Machine. You're kind of unable to unlock some aspects of modern computers easily, like GPUs. And you have this same overhead with respect to memory management. It's possibly a little bit better because you usually don't create so many objects as you might like in Java. But Scala is definitely a language to know if you are in the Java world of big data. So let's wrap up all of this. Python is a useful scripting language, very high adoption rate, which is of course very good when you look for questions and answers in the internet. But the Python environment is kind of easy to break, so be careful, use virtual environments, use virtual machines, use Docker, just to isolate your experiments. R is a fully functional data science environment, and it feels a bit like a classical imperative scripting language, so it's easy to start when you know imperative programming, and it's very powerful in the end. So this is something you should have on the list of things to learn. MATLAB and Octave, if you need matrices and matrix algebra a lot, then you should use them, in my opinion. Otherwise, when you are into other aspects of big data like text or whatever, you should possibly, you can safely avoid those. They are very good for matrices, and therefore also for image processing and things like this, but you might omit them when you're doing text or whatever. C++, if you need to scale up to nearly unlimited performance for your core algorithms, and you still want to have a high quality and very nice language, you should use modern C++. If you only care about performance, you should possibly learn Fortran, but I think this is not a language for this list because it's very fast for very specific tasks, like when you implement linear algebra things, and not in general. So it's a general purpose language, I would say. C++, it's the best trade-off between performance and quality. Java, when you need to scale out, this means you increase performance by adding additional computers. Then Java is the way to go. Most distributed database systems in the Apache project are based on Java just because it's so easy. It's not the fastest in itself, but when you're scaling out anyway, the little bit of performance drawback does not matter, and it's not so error prone, so this is what matters. When you have a system that's possibly 1% slower, but 10% more stable, you will choose it. And Scala, of course, when you have a Java environment already running and you want to have higher order functions and a better or easier parallelism, you should think about using Scala, especially on top of Apache Spark. So that's it for the programming language part. Thank you very much.